Hello guys, this video is on the relationship between the Hilbert adjoint operator T star and the adjoint operator T cross of a operator T. The relationship is given by a theorem which states let H1 and H2 be two Hilbert spaces and T from H1 to H2 be a bounded linear operator. This gives the criterion for the existence of both adjoint operators. Then the Hilbert adjoint operator T star is defined from S2 to S1 and the adjoint operator T cross which is defined from S2 dash dual of S2 to dual of S1, and the relationship is given by the Hilbert adjoint operator T star equals to A1 of T cross of A2 inverse. Yeah, alga correction, A2 inverse, where A1 and A2 are operators from A1 from S1 dash to S1 and A2 from S2 dash to S2. The relationship is shown on the adjoining diagram here. H1 to H2 is the operator T, S2 to S1 is the operator Hilbert adjoint operator T star, and S2 dash to H1 dash is the adjoint operator T cross, and the relationship is T star Hilbert adjoint operator is equals to, from here, A2 inverse to T star T cross to A1, that is A1 of T cross of A2. So this is the relationship between Hilbert adjoint operator and adjoint operator. Now we move on to the proof of this theorem, proof of this relation. To prove this theorem, it is sufficient to find the operator A1 and A2. So first we find these operators A1 and A2. Let F be an element of H1 dash. Then F is bounded linear functional, so F has a Ries representation which is f of x equals to inner product of x and x naught for all x belongs to S1, where x naught is uniquely determined by F, which is uniquely determined by F. So for each F there exists a unique x naught, and this defines a map from H1 dash to H, which is given by A1F is equals to x naught, because x naught is uniquely determined by F. And also we have norm of x naught equals to norm of F, which is given by the Ries representation theorem. So we have defined a map A1 from H1 dash to H1 with the help of Ries representation. Next we find the properties of A1. Now norm of A1F equals to norm of x naught, which equals to norm of F. This shows A1 is isometric, because here norm of image A1F is the image of F and norm of the pre-image are equal, so A1 is isometric. This shows A1 is injective, and by the application of Hahn-Banach theorem A1 is onto. So A1 is bijective. By the application of Hahn-Banach theorem, we have for each functional we can map to x naught, and so A1 is onto, and hence A1 is bijective. Similarly, we can define A2 from S2 dash to S2. Next property of A1 is suppose F1 F2 belongs to S1 dash, then by Ries representation F1 equals to x1, F2 is equals to x2 for some x1 x2 belongs to S1, so that A1 F1 is x1 and A1 F2 is equals to x2 by the definition of the function A1, operator A1. Now the linear combination of F1 and F2 times x is equals to this one by the distributive property of vector space. Then we apply this Ries representation. Then by the property of inner product we have this alpha in the second component alpha conjugate, and similarly beta conjugate. Then we have this one. Now A1 of alpha f1 plus beta f2 equals to alpha bar x1 plus beta bar x2, that equals to alpha bar a1 f1 plus beta bar a1 f2. Alpha bar is conjugate of alpha. This shows a1 is conjugate linear. A1 is conjugate linear. A1 is not linear but conjugate linear. Now similarly for a2, we have for g belongs to s2 dash as a Ries representation gy equals to y naught, where y naught uniquely depends upon g, and we define a operator a2 from s2 dash to s2 such that a2 g equals to y naught. Then as before, a2 is isometric, bijective and conjugate linear. These are the three properties of a1 and a2 which are necessary in the results that follows. Now let us define T star. T star, we define a operator T star which equals to a1 of T cross of a2 inverse. Now we have to show T star is actually the Hilbert adjoint operator. We have defined this operator T star as this relation, and we have to show T star is actually the Hilbert adjoint operator. First we show T star is well defined. Now because this a1 T cross and a2 inverse all are operator, T star is well defined operator. And because this a1 T star and a2, because of the relationship, T star is bounded linear and a2 is bijective, a1 is also bijective, so also a2 and a1 are isometric, and the main result is a2 inverse. A2 is conjugate linear, a1 is conjugate linear times conjugate linear, we get linear. Alpha conjugate, double conjugate gives alpha. So this shows T star is actually bounded linear operator. Linear because 2 times conjugate linear gives linear operator. T star is well defined bounded linear operator. Now finally we show T star is Hilbert adjoint operator. For that we use this relation Tx times y naught equals to y naught. Tx is y, and from Ries representation this is g of y is tx, so this is g of tx. From adjoint operator this is t cross gx which equals to fx. From Ries representation we have x naught, and x naught equals to t star y naught because T star is defined from s2 to s1. This shows Tx y naught is x T star y naught. From the definition, T star is indeed the Hilbert adjoint operator. So the relationship between Hilbert adjoint operator and the adjoint operator is T star equals to a1 of T cross of a2 inverse. This proves our theorem. Thank you.